This presentation, we're going to continue with the sections within Chapter 3 about carbon and carbon macromolecules. So concept 3.2 is about this thing called a macromolecule and this term polymer and how polymers are built from monomers. So basically a polymer is a long molecule that's made up of many little building blocks. A polymer is the train. Monomers are the building blocks that make up a polymer. A monomer makes up a polymer. So the monomer would be the train cars. All the train cars make it a train. Some molecules that serve as monomers also have functions of their own. The way that you can make and break a polymer is basically the same mechanism. So in order to bind two monomers together, we have to take something away so that it can connect, right? And we call this a dehydration reaction. We lose water, we lose a hydrogen and an oxygen and hydrogen so that these two monomers can connect together. In order for a polymer to be broken apart, to make the monomers out of the polymer, we have to add water to it, and we call this a hydrolysis reaction. So I would definitely know what a monomer is, what a polymer is, what a dehydration reaction is, and what it results in, and what a hydrolysis reaction is and what it results in. And then, of course, like with everything, these processes are usually facilitated by enzymes which speed up chemical reactions.
Most biological molecules are very large and are built by assembling small molecules, or monomers, into long chains. The resulting molecules are called macromolecules, or polymers. A process of linking monomers, called dehydration synthesis, involves the removal of two hydrogen atoms and one oxygen atom to form water. One way this might happen is diagrammed here, where several generic monomers are shown with OH groups that could be used for linking. The animation illustrates the joining together of monomers by dehydration synthesis, catalyzed by a polymerase enzyme, and the reverse process, in which added water results in hydrolysis, catalyzed by a hydrolase enzyme.
Okay, so hopefully you saw that. That enzyme came in, it took out an oxygen and a hydrogen, and it made it a monomer into a polymer, and then we added water to it to turn the polymer back into a monomer. So here you can see the same thing. You have a short polymer here, you have an unlinked monomer here. Take out the oxygen and the OH, spit it out, and that makes water, H2O, and now you have a longer polymer. Now I want to break this up again, so I'm going to introduce water to this bond right here, and you end up with a short polymer and then that unlinked monomer. Each cell has thousands of different macromolecules inside of it. Every single tiny cell that we have has thousands of macromolecules. Macromolecules vary among cells of an organism, vary more within species, and vary even more between species. An immense variety of polymers can be built from a small set of monomers. And one way to think of that, why that is if you think about just the alphabet alone, there's 26 letters, which make up millions of words. And then even within those words, the way that you arrange those words into sentences have different meanings and provide different communication. So the four types of macromolecules that we're going to learn during this chapter are carbohydrates, lipids, proteins, and nucleic acids. First one we're going to look at are carbohydrates. Carbohydrates are sugars, and then there's sugars that are monomers, and then there's polymers of sugars. Simple carbohydrates are called monosaccharides, or simple sugars. These give us quick energy, but it doesn't give us sustained energy. So carbohydrate macromolecules are polysaccharides, polymers composed of many sugar building blocks. So in a carbohydrate, the monomer would be a monosaccharide. When you put a whole bunch of monosaccharides together, it makes a polysaccharide, which is the macromolecule. Monosaccharides have a molecular formula that usually is some multiply of CH2O. So with glucose, we have 6 carbons. So 6 times the 2 hydrogens there make it H12 and then O6. It's the most common monosaccharide. Glucose is sugar, right? It's what you sweeten your tea with and add to cakes and cook with. Basically, it's cane sugar. Monosaccharides are classified by the number of carbons in the carbon skeleton and the placement of the carbonyl group. So if you look at 3 different types of monosaccharides, C3H6O3, then that's a triose, a 3-carbon sugar, and it's called glyceraldehyde. Then you've got pentose, which is a 5-carbon sugar, H5H10O5. It's called ribose. And then hexose are 6-carbon sugars, and there's 2 different types of them, glucose and fructose. And just where that oxygen is attached to it makes them 2 totally different types of sugars. Glucose being in like cane sugar, fructose being what sweetens fruit and other things. And both of those are energy sources for organisms. So even though, like in the previous picture, we're looking at them and it looks like they're drawn as linear skeletons, when they're in a water, an aqueous solution, the sugars will wrap around and they'll actually form rings. That's what makes them happiest. And so monosaccharides serve as major nutrients for cells and as raw material for building molecules. So monosaccharides are the building blocks to make polysaccharides, which are the macromolecules. Monosaccharides is a single circle of a carb. A bunch of those grouped together make a polysaccharide. A disaccharide is formed when a dehydration reaction joins 2 monosaccharides together. This covalent bond is called the glycosidic linkage. This is a really important slide. A monosaccharide is a single ring of a sugar. When you have 2 single rings of a sugar and you take water out, you have grouped them together, and now you have a disaccharide. You have 2 of them, very tiny polysaccharide. The bond that links the 2 monosaccharides together, what makes a disaccharide from 2 monomers, from 2 monosaccharides, is taking out water, dehydration reaction, causing a glycosidic linkage in them to link together. I would know what glycosidic linkage is. I would know a dehydration reaction. I would understand that 2 monosaccharides make a disaccharide. I would understand that multiple monosaccharides with multiple dehydration reactions and multiple glycosidic linkages make a polysaccharide. So let's watch this animation of making a disaccharide.
Sometimes organisms link sugar molecules in pairs to form disaccharides. Here are several examples. Plants make sucrose by joining glucose and fructose. Sucrose circulates in plant sap, and we obtain it from sugarcane and sugar beets and use it as table sugar. Lactose is formed by joining galactose and glucose. Lactose is the disaccharide that gives milk its sweet taste. Maltose consists of 2 linked glucose molecules. Digestion of starch, in a sprouting seed or in the intestine of an animal, produces this disaccharide.
Now, I don't care that you know what sucrose, lactose, or maltose is. I'm not going to ask you to write this, but what I do want you to understand is how they're made, right? Hopefully you saw that the water was taken out and that you know that this linkage right here is the glycosidic linkage.
Sometimes organisms link sugar molecules in pairs to form disaccharides.
So here is the same image over again, glucose and fructose to make sucrose. We had the dehydration reaction occurring right here. We had to take oxygen out, you had to take a water molecule out in order to give them the ability to hold hands. And holding hands right here is called a glycosidic linkage. Polysaccharides are the polymers of sugars. We've said this a million times before, and they have storage and structural roles. So polysaccharides are going to have a lot more energy storage than a simple monosaccharide is. It takes a lot more to break them apart to provide us with more energy. The structure and function of a polysaccharide are determined by its sugar molecules and the position of the glycosidic linkages. Starch is a storage polysaccharide that plants have, and it consists entirely of just a ton of glucose monomers. So plants store surplus starch as granules. Most animals have enzymes that can hydrolyze plant starch, not start, but starch, making glucose available as a nutrient. So most animals, including humans, have an enzyme that can break that starch molecule up so that we can use it as energy. It's very, very, very complex. Starch would be found in pasta, flour, other things like that, and that's why like a marathon runner would do a carb loading, a week or so before the marathon, because he wants to load up on carbs so that he gets a quicker release of energy, but kind of a longer residual type release of energy, faster than say fats or proteins, but still going to be released slower than if you like pop a sugar cube, then you're going to be hyped up, or you drink a soda, you're going to be pretty hyper for a little bit, and then you're going to crash. Glycogen is a storage polysaccharide in animals. Humans and other vertebrates store glycogen mainly in the liver and muscle cells. So, when you have when you eat, your liver actually will release enzymes to help break up that glycogen for you, and some people have issues where they don't have enough of that enzyme.
Polysaccharides are polymers, long chains consisting of hundreds to thousands of linked monosaccharides.
Another polysaccharide, cellulose, is a major component of the tough wall of plant cells. So it's like starch and glycogen. Cellulose is a polymer of glucose, so it's a lot of glucoses linked together, but the glycosidic linkages differ, which make it cellulose. And the difference is based on the two ring forms for glucose. So we have an alpha and a beta glucose. Alpha glucose, it's all about where that other hydroxide element is right here, sticking up at the top or closer to the other one. And so it makes it have with starch, with the alpha glucose, all of the OHs are along the bottom of the rings, whereas the beta in cellulose, it's mix matched. So in starch, glucose molecules are arranged in an alpha conformation, and in starch, it's a beta conformation. So cellulose molecules are relatively straight, like it's going to be straight across. Starch is going to be kind of zigzag. Cellulose is going to be straight across because these guys aren't competing with one another. They're far enough apart that there's no electric or positive and negative forces pushing them. Parallel cellulose molecules held together this way group in these big microfibrils, so that they'll just be stacked one on top of the other, making a huge microfibril, and that forms the strong building materials for plants. That's why trees can be as tall as they are without flopping over. That's why the plants can get very tall, even flowers, and still seem kind of flimsy but not fall down. Roses have real thick bases, etc., etc. Enzymes that digest starch by hydrolyzing the alpha linkages can't hydrolyze the beta linkages in cellulose. So if you can digest starch, you can't digest cellulose. So for humans, we can digest starch just fine. We can digest it, we can store that energy, but we cannot digest cellulose. Instead, it's fiber. So we eat fibrous materials, it goes through the digestive tract. Fiber is good for you because you can't digest it. It scrapes your colon and all your digestive tract, and it kind of cleans it out for you. And that's why fiber is supposed to be cleansing for the colon. Some microbes, though, will digest cellulose. So animals that eat a whole lot of grass and cellulose material, like cows and even termites, will have some sort of a symbiotic relationship where inside of their gut, they have these special microbes. And so the microbes eat the cellulose for them and digest it, and then the cow and the termite's gut is able to absorb it based off of pretty much the excrement of those microbes. Chitin is another structural polysaccharide that we cannot digest either, and this provides support for the cell walls of fungi, but it's also extremely important in the exoskeleton of arthropods. Arthropods being spiders, insects, all the crustaceans, millipedes, centipedes. And so what makes them all have that really hard shell, the skeleton on the outside, the exoskeleton, is this strong chitin that allows them to be very rigid and hard, and why that cockroach crunches when you step on it. Why it's hard to peel the shell away from the tail of the lobster. Okay, now we're going to move into concept 3.4, which is about lipids. So we learned about carbohydrates. Now we're going to learn about another type of organic molecule, macromolecule, that's important to the makeup of our bodies and other living things, and that's lipids. One thing to know about lipids is that of the four groups that we're going to look at, they don't really form true polymers. A unifying feature of lipids is that it has little to no affinity for water. It doesn't like water, and so we call them hydrophobic. They consist mostly of hydrocarbons, which form nonpolar covalent bonds. So it's like these long tails with a lot of hydrogens coming off that don't like to be around water at all. Oil and water doesn't mix. That's a lipid. The way that it bubbles up and tries to make the smallest amount of surface area it can instead of spreading out, separating itself, you see that when you try to mix oil and water together. The most biologically important lipids are fats, phospholipids, and steroids. So we're going to look at those three types of lipids.
Butter, lard, margarine, and salad oil are composed of lipids called fats. To make a fat molecule, 3 fatty acids bind to a molecule of glycerol. For this reason, fat molecules are technically called triglycerides. Fat molecules do not mix with water because they have 3 long nonpolar hydrocarbon tails. Cells use fats for energy storage because the tails hold more potential energy than other biological molecules. The fatty acid tails in a fat can vary in length. A very important characteristic of fats is the number of double bonds in the hydrocarbon tails. Fats that contain only single bonds are called saturated fats. Fats containing double bonds in one or more tails are called unsaturated fats. Unsaturated fats tend to be liquid at room temperature. Vegetable oils are examples. Saturated fats, like butter and lard, are solid at room temperature. Saturated fats in the diet can lead to heart disease, while unsaturated fats are safer.
Okay, so that was a really good overview video of what a fat is. So fats are constructed from 2 types of smaller molecules, that glycerol head and then fatty acids, right? This one has 3 fatty acid tails and the glycerol, which is kind of like the head of the train. Glycerol is a 3-carbon alcohol with a hydroxyl group attached to each carbon, and then the fatty acid consists of carboxyl groups attached to long carbon skeletons. So here's our carboxyl groups, the long carbon skeletons in the fatty acids, and then the 3-carbon alcohol with the hydroxyl group, 3-carbon alcohol with the hydroxyl group on the end. And so get rid of, do a dehydration reaction, get rid of water, and then you form this link. This link is called an ester linkage. Carbohydrates, it was a glycerol linkage. So an ester linkage is what connects the fat, makes a fat molecule, a triglyceride. It connects the glycerol to the fatty acid tail. Fats separate from water because water molecules will hydrogen bond to each other, and that excludes the fats. So it kicks them out of the way. And in a fat, the 3 fatty acids are joined together to glycerol by an ester linkage or a triglyceride linkage. Another term is triacylglycerol. So know both of them. They both kind of look the same, but you're not going to get a trick where you have to choose this one from the other. So that triglyceride linkage is similar to what the carbohydrates had to have. Fatty acids vary in length, depends on how many carbons they have, and in the number of locations of double bonds. So you saw from that video that if it had a double bond, it kinked off, and so it had a little kink in it. And that if it has a kink in it, it becomes an unsaturated fatty acid. It has 1 or more double bonds. Saturated fatty acids have the maximum number of hydrogen atoms possible and absolutely no double bonds. And that makes them worse in a way because they're able to just really cram up next to each other. Unsaturated fatty acids have all these kinks in it, and so they spread out from one another. So saturated fatty acids, fats made from saturated fatty acids are called saturated fats. They're solid at room temperature like butter, and most animal fats are saturated. Unsaturated fatty acids have the double bonds in it. Fatty acids, fats made from these fatty acids include plant fats and fish fats and are usually unsaturated. So vegetable oil, fish is healthier for you than having steak every single day because you're getting unsaturated fatty acids instead of just saturated. And we call them unsaturated fats or oils. They're liquid at room temperature. So here you go. Here's butter, just all crammed up next to each other, becomes very, very solid. But you have just one little double bond in there, and it causes a kink in the system, and so they can't cram up right next to each other, and they become an oil. The major function of fats are to be energy storage. So when you eat way too much fat, more than your body needs in a given day, it will start to store it. Fat is a compact way for animals to carry their energy stores with them. So beluga whales and walruses and bears that have to hibernate are going to eat a whole lot of fat to store it up, or they need more of a layer blubber so that they can be warmer in the water. Fats are an important part of our diet. We should include fats in our diet, but you just want to not overload yourself with too many fats, and especially not saturated fats only. So fats are a type of lipid. Phospholipids are another type of lipid. A phospholipid is two fatty acids, so two tails, and a phosphate group attached to a glycerol. The two fatty acid tails are hydrophobic, but the phosphate group and its attachments form a hydrophilic head, or it likes to be around water. Phospholipids are major constituents of cell membranes. So, because the way that a phospholipid looks, it has the two hydrophobic tails. It can have kinks in them. Doesn't always have to, but it can have kinks in them, and most of them do. And then the tails are hydrophobic. They're afraid of water. Hydrophilic means I like to be around water. And so it's made up of this glycerol. Off of one of the carbons is connected to a phosphate group or a phosphorus group. And then there's functional groups that stick off of that. So this whole head likes to be around water. And so when these guys get together, the hydrophilic heads will pop out and touch wherever the water is. But the hydrophobic tails don't want to be near water. And so as a result, they'll flip upside down, and the hydrophobic tails will touch one another and make this layer. And so we call it a phospholipid bilayer because it's two layers of phospholipids, with the hydrophilic head being near the water on both ends, and it makes a perfect barrier. It makes a little fence or a perfect barrier, and it's a major component of a cell membrane. So now it's totally encompassed the innards of a cell, and it keeps certain things in, keeps certain things out, and it allows certain things to come and to go. So phospholipids are extremely important component of cell membranes, make up cell membranes. When phospholipids are added to water, they self-assemble into that bilayer, hydrophobic tails pointing towards the inside and hydrophilic heads towards the outside. Now, steroids are the third type of lipid to know, and so they're basically a carbon ring consisting of 4 fused rings. So cholesterol is a really important steroid. It's a component in animal cell membranes. Too much of it isn't good for us, but we do have to have some cholesterol in our diet. Although cholesterol is essential in animals, high levels in the blood contribute to clogging of your arteries. So this is what cholesterol looks like. It's got 4 carbon rings all attached to one another. And then things can come off of it that make all the different steroids different. I showed you testosterone and another steroid in the previous presentation for chapter 3, kind of the intro part. And there were different elements coming, or different components coming off of this element to make every steroid different. But this is the basic look of what a steroid is. So we're going to stop here and continue with proteins and nucleic acids in a separate section.